face to face. Sometimes you got to face to face. In this video, we are going to face the body-centered cubic 1-1-1 face. Recall that in the body-centered cubic structure, we have one atom at each of the corners of a perfect cube, and the edge length we define to be A. So this is just a generic parameter that is different for different metal crystal structures. The angles are all 90 degrees, so we have a perfect cube, but also we have an additional atom of exactly the same type as at the vertices in the center. For the 1-1-1 face, we can visualize that as connecting this corner point, and that corner point. And we see that they're outlined with these orange lines. And then if we look vertically upon this shape, we see that we have an equilateral triangle. For this equilateral triangle, the length of each side is exactly the same, and it is the square root of 2 times A over 2. If we extend the lattice in this direction, each by a step of square root of 2A over 2, and also in this direction by the same amount, and extend the lattice infinitely, we get a shape that ends up looking something like this. In the extended lattice. We notice, at least superficially, that this looks just like a hexagon. So whenever we have a lattice made up of these equilateral triangles, the extended structure will resemble a perfect hexagon. If we extend the structure and look below, we would notice that in the center of the equilateral triangle, but at a lower level, that's why I'm writing it as that open circle here, we have another atom of exactly the same type. So let's imagine that our BCC structure here is iron. So if this is iron 1-1-1, all the atoms I've shown here in filled in black are all at exactly the same height. And then below the level of the black filled in circles is another iron atom that is at a lower level. And its actual height is going to be the square root of 3A over 2. But the important thing is that this is not at the same level as the sort of 3 on the outside of the triangle. Similarly, there will be central atoms below the surface at exactly the same height as here, over here, and over here. So they may or may not be clearly seen that these are supposed to be open circles, but let me kind of just to make that clearer that that's an open circle. That's an open circle as well. So this triangle, and this triangle, in the center, there is another iron atom at this lower level. Then similarly, there isn't one at the same level of here, here, and here. There is not one in the center there, there, and there. There'll be one another level below. So while the superficial external outermost layer of the 1-1-1 will be all this sort of triangles that eventually makes a hexagon, there are also other iron atoms that are subtly below the surface in 2 different possible layers. So that the 1-by-1 rectangular bricks that model the surface of the crystal structure will fit exactly into the base at precise locations, we can model this 1-1-1 surface as follows. So let's divide the base into 2 regions that are each have a length of 4. So we have 4. Now this length is going to be a length of 7. So essentially we have a right triangle with one side being 4, the other side being 7. And if we do that, we notice that this length, as we've seen before, has a length of the square root of 65, which is only very slightly larger than exactly 8, which is the length of this side. So if we model the 1-1-1 surface by using this distance of 4 and 7, it models the threefold symmetry within sort of the experimental error of the fact that whenever we have these kind of crystal structures in reality, they very often vary slightly from the theoretical predictions. So within the uncertainties of experimental error and the changes that occur in real crystals as opposed to ideal crystals, this is a very, very close approximation to the actual surface structure for iron 111. Once we've gotten this far in modeling the body-centered cubic 111 structure, with minor changes, we can model the cesium chloride 111 crystal phase. So, if we have our body-centered cubic unit cell over here, we've replaced the identity of the body atom, so now it is green. So let's imagine that this green atom is chlorine, and that the black atoms at the vertices of the cube are cesium. So here we have our cesium chloride structure. Again, we've connected the surface atoms of the plane that we're looking at, the 111 plane, with these orange lines. So we notice that the three atoms that are connected by the orange lines are all cesium. So here we have cesium, 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 and our extended surface, our 111 cesium chloride surface, would only have cesium atoms at the surface. So, and if we just simply swapped the identities of what we're calling cesium and chlorine, so if now we said that the green atom was cesium and the black atoms were chlorine, then our 111 cesium chloride surface would be entirely chlorine terminated. So no matter which atom we have, when we have the cesium chloride 111 surface, it will be monometallic. It will only have one element. It will be one or the other depending upon how it's been cut. So it shows that we could have two possible ways of slicing through our cesium chloride in such a way to get the 111 surface, one of which would be cesium terminated, one of which would be chlorine terminated. As we had mentioned with the body-centered cubic case, in the center, so to speak, of this equilateral triangle, we have the body-centered atom that is at a lower level. Now, since we're doing cesium chloride here, and let's just say that black is cesium and green is chlorine, then we have chlorine atom here. But this chlorine atom is below the surface, so even though I've filled it in as filled in green, interpret this particular atom as being below the surface of the black atoms. And there would also be another chlorine at exactly the same relative height here and here. So at the center of this triangle, this one and this one, that might be more accurately put. Here. So our top layer we have black, which is cesium. Then below we have a layer here, here, and here of green atoms. Then we'd have another layer below where we'd end up having the iron atoms again, and then another layer with the chlorine, which would be the cesium, and then we'd have chlorine atoms here, here, and here. So we notice that sort of in between, if we think of this as a hexagon, that in the next layer we'll have this sort of alternating triangular shape, which will be clearer once we model this with Lego. Three carbon monoxide molecules adsorbed onto body-centered cubic 111 face on top, here highlighting the threefold nature, the C3 nature of the 111 surface. Here the arrangement of adsorbed carbon monoxide molecules is to highlight the six-fold rotational symmetry of the surface. Here we see figure 6, which shows the layout and dimensions of the body-centered cubic 111 surface. So we notice poking through our punched out holes here, we see the gold tips, the studs. So these are the underlying metal atoms from the body-centered cubic 111 surface. And we notice that the distance between two adjacent atoms along the surface is the square root of 2 times A over 2. And it's identical because this is an equilateral triangle. One thing to remind ourselves is that below the level, these filled in circles are below the level. So these are different colors to show us that it's not of the same type and it's not at the surface. So but we notice that kind of in a threefold hollow here, so below here, below the surface, there will be an atom. Now, there will be an atom here also, but it's even further below. So this one, and this one, the ones that are shown, are the next lowest level below the exposed level that we see with the gold painted bricks. But there's also equivalent atom to this one here, but it's not at the same level as this, and this. So we see that once we try to be even more particular about how we model the surface, then certain details of the subsurface, the near bulk to the surface, can become important. So we see here with the 111 surface, we have the smallest repeating unit we see is an equilateral triangle, but also we see the overall six-fold symmetry of the regular hexagon. Since this structure is even more extended than previous structures that we had shown, in the sense that we have a bigger 2x2 space that we've taken up, we can see how useful these figures are to figure the structure. So we see here we've used two different figures, and we notice that by using multiple figures, that if we repeat the figures, kind of extend, we can extend this identical structure as large as we want. And that conveys the idea quite well of what a lattice really is. For any of the structures that we have, if we make multiple copies of the figure template, then just by putting them on top of each other and extending in both the x and y directions, we can build up any surface we want. We can use the figures and parts of the figures to verify the various symmetry operations of our surface. We can use this piece here to verify our threefold rotational axis. And we're helped by the fact that we have these circles here to remind us of our original orientation. And so we know that we have a gray circle at the top. Now if we try to do a C6, we rotate by a sixth of a turn here, all the atoms do line up of the exposed part of the surface. All the golds will be exactly in the same locations. But we see that the grays have moved, the next lowest layer. So if we just try to rotate by a C6, that's what we started with. After we rotate, the gray goes from there to there. It's not exactly the same. So if we include the subsurface parts, include the bulk, then as far as this surface goes, it does not have a C6 rotational axis. But again, if we start with this, the gray being at the top, now if we rotate by a third of a turn, we get to here. Not only will the gray atoms at the corners and the center all line up perfectly, but also even the gray atoms are now. So our hexagonal orientation of atoms looks exactly the same as it did before we started. So it's since it's invariant under a C3, under a 120 degree rotation, we say the surface has the C3 symmetry operation. So it has a C3 high order rotation axis. So then we can verify, for example, C2s and such with these. So we just simply take our template, line it up over a collection of atoms, perform the symmetry operation, so for example, do like a C3, and see if the atoms all line up. If they all line up, and the subsurface also lines up, then we do have a symmetry operation. If we ever have a situation where one of the holes isn't filled, or that they're trying to fill a hole that isn't there, then we know that that particular symmetry operation is not an operation of the surface. So by using the figures and parts of the figures, we can verify, for example, translation. We pick it up and we move it along a certain vector. It repeats. And we can also verify rotational axes using the same ideas. I thank you very much for your attention. Have a good one.